Hello, everyone. Welcome to our second edition of the event Understanding Deep Learning. The subject of deep learning has become one of the main focuses of study for many researchers around the world, who are expanding the frontiers of the state of the art with new methods on a daily basis. However, this subject is still mystified and little known technically by much of the general public. The data group has therefore proposed an event that will include researchers and professors from renowned universities in Brazil and abroad in order to really understand how and why deep learning works. This event aims to disseminate and promote science, encourage new researchers, as well as giving free access to quality knowledge in the field of artificial intelligence. This event is organized by Data, a student data science group at the University of São Paulo in Brazil, which I coordinate. I would like I'd first like to thank the University of São Paulo and the Institute of Mathematical and Computer Science for the support in organizing this event, and, of course, to thank Sebastian Ruder, our first speaker of the event. Sebastian Ruder is a research scientist based in Berlin, Germany. He leads the Multilinguality team at Cohere, whose mission is to improve the multilingual capabilities of Cohere's large language models, LLMs. Before that, he was a research scientist at Google DeepMind. He completed his PhD in natural language processing at the Insight Research Center for Data Analytics. While working as a research scientist at Dublin-based text analytics startup AYLIEN. Previously, he studied computational linguistics at the University of Heidelberg in Germany and at Trinity College, Dublin. Before we begin the talk, I'd like to give a brief message to the Portuguese speakers. Oi, gente, tudo bem? Essa palestra vai ser ministrada em inglês. Caso você tenha dificuldade em acompanhar a palestra, não se preocupe. Depois de finalizada, a palestra ficará gravada no nosso canal e ficará disponível com a opção de tradução automática. Infelizmente, demora um pouco para o algoritmo processar e gerar essa a tradução automática, então espere um pouco, até o final do dia deve estar disponível já. Eu agradeço a compreensão de todos. Okay, before we begin, Sebastian has a blog, which I strongly recommend you to check it out. It's called ruder.io. So later, check it out. Okay, Sebastian, shall we begin?
Sure, yeah. Hey everyone, it's great to, thanks for having me. It's great to get the chance to chat to you about language models and multilingual evaluation. Can you see my screen? Do you need to share slides? Yeah, okay, awesome. Cool, yeah, so in my talk today, I want to tell you a bit about some challenges and limitations when evaluating large language models in practical real-world use cases. And so to get things started, as Theo already mentioned, I work at Cohere, and to give you just kind of a bit more context about the work that we're doing at Cohere. The Cohere is a startup that focuses on developing foundation models that are specifically suited for business applications. And we make these models to be multilingual. We focus on 23 languages in total, and with an emphasis on these 10 priority languages, among Brazilian Portuguese being one of them. You might have seen, if you're doing research with large language models, you might have seen or maybe heard about some of the models we released this year, which all of them, because they are released as open weight models, can be used for research. Some of the models that we released, for instance, are Command R and Command R+, which was, upon its release, the top open weights model on the Chatbot Arena leaderboard, if you've heard about that. And we also recently released updated versions of these models in August. Cohere also has a dedicated research lab called Cohere for AI, which has focused on developing models that are much more multilingual, and which include AYA 101, which covers 101 languages, as well as a recent AYA model that covers 23 languages. And for the work that we're doing at Cohere, specifically the work that the multilingual team is doing, because multilinguality really spans every component, every part of the language modeling pipeline. We work both on pre-training all the way to adapting models to specific customers with the corresponding teams. And parts that kind of span all of these components are data, so kind of ensuring that you get high quality multilingual data at every stage of the model training, as well as making sure that you have proper evaluations and proper metrics in place to be able to identify limitations early on and to hill climb and optimize the right metrics. And so for this talk, I want to talk a bit more about how or in what kind of ways we can evaluate these large language models in practice. And to give a bit more context, if you're not that familiar with the current state of large language models or how they are evaluated in the community, I want to just share a few, in my mind, kind of larger trends about evaluating NLP models and large language models more recently. And specifically, one of the kind of most established tasks in natural language processing is machine translation. And machine translation is something that has almost 50 years of history. And in this task, one of the most widely used metrics is known as BLEU, which just measures token level word overlap between the translation and the gold reference. And as you can imagine, given that this task has been very popular, also a lot of other metrics have been proposed over the last decade, for instance. However, even though this standard metric BLEU has its limitations, and even though many metrics which are arguably better have been proposed, still, in prior studies have found that over the last decade, most research papers still use this established, simple, easy to compute metric. So in practice, as a community, it can be quite hard to move away from metrics that are established and easy to use if given their wide use and adoption. The other point for data sets and kind of benchmarks that are developed in the field is that given the capabilities of our models have really been rapidly increasing over the last few years, and as a result, benchmarks also easily become saturated. So if you look at this graph, for instance, which basically compares the performance on a lot of standard benchmarks in ML and NLP until the level, so from the level of initial performance of the initial baseline in the paper to the level 0.0 when they reach human performance. And you can see that for standard ML benchmarks like MNIST, it took almost 20 years for models to actually reach human level performance. But for more recently proposed benchmarks like Squad or GLUE, the half-life time or the time to actual human level performance has been only much shorter, a year, or in some cases, or even a few months. And this is a challenge even for new benchmarks, which have to be continuously harder and more challenging to make them still challenging and difficult enough for current models. So in the current evaluation landscape of large language models, there are a number of established benchmarks. Some of them you may know perhaps, like MLU, which consists of exams across different categories and different disciplines. There are benchmarks like GSM-8K that evaluate mathematical problem solving, or benchmarks that evaluate code reasoning on code or code generation. But many of these benchmarks still have their own issues. For instance, because some of these have been around for a while, recent work has found that there's models have started to overfit on the test data. These questions are being trained on similar data, or maybe some of that data even leaking through training. And for the most recent or the current set of evaluation metrics that are being currently used in practice, like Chat Ballerina, which is essentially a crowdsourced way of having people A/B test different model generations from different models and kind of compare which performs better, or using models to perform evaluations themselves. These have been recently become popular, but they also have their own problems. So for Chat Ballerina, for instance, studies have shown that people still can be susceptible to certain biases. For instance, if you see a response that is nicely formatted with nice markdown headings, and different formatting in paragraphs, you're more likely to give this response a higher rating. So yeah, with that, I just want to highlight kind of some of the pitfalls and challenges when evaluating large language models to date. The other point I want to mention here when it comes to evaluating multilingual models is that the performance of these models is not the same across languages. So to give one example here, if we look at the performance on this MLU benchmark of exams that I mentioned at two recent representative models, Llama 3.1 and Claude 3 Solid, we can see here the performance on the English benchmark. And now for evaluating these multilingual models, what is commonly done by many of these, many of the companies or institutions that train large models is to evaluate them on translations of these established English benchmarks. So in this case, there's also multilingual versions consisting of translations of the English MLU exams. And if we look at the performance on these benchmarks, we can see that there's generally a gap between the English performance and the performance on the multilingual subset for most models. Now, if we look at the larger variants of these models, so the larger Llama 3 and the larger Claude 3 model, we can see that that gap in terms of from English to multilingual performance generally has reduced with increasing scale. And we can see the same pattern for translations of other benchmarks, like for MGSM, which is a translation of the math word problem benchmark GSM-8K, where we can similarly see reducing benchmark multilingually once we evaluate the larger variants of these models. However, one downside or one limitation of these kinds of relations is that they only evaluate models on translated data. And in practice or in the field, this kind of translation data is often called translationese because translated data doesn't actually or doesn't truly reflect natural data that will be uttered by native speakers. So it's different in subtle ways. And so it's not really like an accurate reflection of the actual natural language that we want our models to generate or evaluate in the end. And in addition, because this translation data is from English-based exams, it also doesn't really represent the actual content or the actual knowledge that we would think to be reflected in other languages in the corresponding cultural setting. So here, basically, just want to highlight a couple of additional points that I think are currently not being truly reflected in the current array of multilingual LLM benchmarks. And in order to really like faithfully and properly do multilingual evaluation, we really also need to take into account the needs and the given constraints of people that speak different languages. And that may have different information needs, right? So someone who is in the US may be very interested in baseball or American football statistics or questions, whereas people in Brazil may not really care about that. And similarly, there's also different types of cultural and common sense knowledge that is required or known to be true in other countries. And the same thing goes for values and norms, which can differ across cultures, as well as what is considered taboo or even misogynistic in terms of hate speech. And while there have already been useful advances in these directions in terms of research, these still need to become kind of more widespread and more widely adopted. So for the remainder of this talk, I want to talk and highlight two topics in terms of practical challenges and current limitations of models when evaluating them in multilingual settings. With the first one being kind of in a standard conversational setting, and the second one being when we apply quantization to these models. So we want to use them in resource-constrained environments. So for the first part of this talk, I want to talk about conversational language and evaluating the conversational ability of models. And here, just kind of on a general setting, right? If we interact with an agent and an LLM, and we want to evaluate its ability to actually meaningfully participate in the conversation, there are, I think, two aspects that are particularly important, right? We want it to generate a response that kind of understands our intent and the intent of our initial message, and that is appropriate both in terms of the content, right? We don't want it to hallucinate or to make things up or to be overly verbose. And we also want the form of its generation to be correct, right? We want it to use the right grammar, to have the right like dialect or style, talk with us in kind of an expected tone or register that we would expect from a language model agent. And in the kind of current space of research on these conversational evaluations, there's been a lot of attention focused on how we can evaluate the truthfulness or the content or the faithfulness of a generated response, right? So you might have heard of things like hallucinations, right? That models are often likely to imagine, to hallucinate, or to make things up, and that in practice we want to reduce this amount of hallucinations. Yeah? And that's one angle or one type of deficit or model limitation that we want to eliminate. But similarly, we also care about, and so far, comparatively few work has focused on the content aspect here, right? So making sure that the form, the style, and the tone of the model is correct. And because errors along this dimension similarly can lead to poor user experience and to breakdown in trust. And for this project and the evaluation that I want to discuss here, we focused on one very basic kind of fundamental angle of form errors in multilingual conversations. And in particular, we focus on the model's ability to generate text in the correct language or the correct language given kind of conversational context at that point. And we found, to our surprise, because in practice, a lot of these models, you can interact very well with in your own language. We still found that even for state-of-the-art models, they're surprisingly, or in like more often than we expected, unable to consistently generate text in the language that we would require of them. And we termed this phenomenon, this error behavior, language confusion, in order to also contrast it to kind of more the natural form of switching between languages, which is known as code switching. So typically, right, if you talk with people in different languages, you might code switch between English and Portuguese, for instance, which is typically fine and which we would probably be okay with our model in doing. But in these cases, we observed code switching or language confusion in ways that humans would definitely not do, and which is very unexpected and can lead to poor user experience. And to give some examples of how this looks like, here you can see a user request in Korean, and the model, which is Command R in this case, responds in fluent Korean. However, at some point, it arbitrarily switches to English or mixes in an English word in the corresponding response. And while the rest of the response is correct, and the English word actually, when you translate the generation to English, also makes sense in context. So it's semantically correct, just happens to be in the wrong script in the wrong language here. Or we can also see this behavior with other models that have been released more recently, like Llama 3.1, for instance, where we have another user query in Russian, and the model, again, generating correct response in Russian, and then also seemingly arbitrarily switching to English for a few words, while then continuing later the rest of its response in proper Russian. So you can already kind of see that this behavior can be exhibited on different levels. We found the most compelling and the most challenging to detect case is this detecting this behavior on the word level. But we also found this on the line level, or kind of most obviously on the level of the entire response, where the entire response would be in different language. And so because we didn't really find any existing evaluations or any existing data sets to evaluate or test for this behavior, we developed our own by curating a set of prompts from different sources, including different multilingual data sets in different languages, as well as using our own prompts from data that we had collected internally. That are more complex, so that represent more challenging or more complex instruction following behavior. And just to reflect kind of a different set of use cases and different complexities and levels also of nativeness of the prompt, going from human-generated data to machine-translated generations. Now, the settings that we evaluated our models in are basically the standard kind of the standard setting that you would use if you interact with a language model in your language, where you just query the model in your language and you kind of implicitly request an answer in the same language that you post your query. But we also evaluate a different setting that we term cross-lingual generation here, where we explicitly instruct the model to generate text in different languages. So the instruction or the initial prompt here would be in English, and we add to this English prompt an instruction instructing the model to generate in different language, like you can see here, where the model is instructed to generate an essay in Korean, for instance. And this setting is kind of relevant because for, as I mentioned before, Cohere serves different businesses. And for some of these businesses, they have customers all across the world. So they want to serve customers also in different languages. And so for a particular application where they want to integrate a language model, they don't really want to have a prompt instructing the model to generate for each language, but want to have a single prompt, usually in English, where they can just swap in and out the corresponding instructions in which language to generate in. So for these kind of scalable use cases, it's very important for the model to be able to follow this explicit language instruction. Now, in terms of evaluation metrics, we initially thought about using standard metrics like accuracy or F1 that are widely used in the community, but then switched to using instead binary metrics, right? Because we realized that for the actual user in experience, it doesn't really matter if there's one word or two words code switched or one line or multiple lines in an otherwise quite long response. What mainly matters is if there's any code switching or any language confusion going on at all. Because if you see like a single word error, you already start to lose faith in the generated response. Yeah? So because of that, our metric here is basically just a percentage of model responses where all the lines are in the correct language. And what we use here for identifying whether a generated line has the correct language is just an off-the-shelf tool for language identification developed by Facebook called FastText, which kind of in our initial experiments and in studies has been shown to be very efficient, but also very relatively accurate, as long as the lines are long enough that you apply it to. Similarly, we also perform evaluation on the word level. And here also on the word level, we mainly focus on responses where all the lines are, where all the words are identified to be in the correct language. And additionally, we exclude all lines that already have errors, because for every line where there would be, which would be in different language, all the words would also be in different language. So for the word level metric, in order to really disentangle both the line level and the word level precision, we only focus on errors or on lines where all the words, all the lines are already in the correct language. And in this case, we first looked for using language models or other fine-tuned models for evaluation, but realized based on prior studies that this problem of detecting whether, kind of in general, whether a word in a text is in the correct language or not is very difficult, right? You can imagine this. A lot of European or Latin script languages, for instance, have loan words from other languages. So actually detecting at a very high precision level whether any of these words is in the correct language or not is kind of very difficult to do at scale. So in this setting, to make this actually tractable, we instead focused on settings where we can still do this evaluation, but with a higher precision. And here, this basically meant that we try to rely on heuristics instead. So we found that for languages that don't have a Latin script, so in our evaluation, this is Chinese, Korean, Russian, and Arabic. We found that the primary language where they would switch into on the word level is in English. So instead here, we basically rely on using a word list that we have filtered to remove false positives and basically detect whether there's any occurrences of English words that come from this word list, which are most likely to be word level errors in our evaluation. And similarly, for the Latin script languages, we just focus on the setting of detecting whether words are in a different script or use any accents or other types of diacritics that are not seen in the original language script. So just looking at the Unicode range of each token in the word for making this judgment. Now for our evaluation results, we focused on evaluating models from 4 different model families. Llama models, models from Mistral, from Cohere, and from OpenAI, GPT models to the right. And here you can firstly see kind of the case for monolingual generation. So we have the prompts in the same language as we would expect the model to generate in. And we basically just for our experiments here used kind of the same parameters across all settings. And we use a standard sampling algorithm called nucleus or top P sampling, where instead of sampling from the full distribution of the next token outputs, we instead sample only from the top P words whose probability together sums up to 75% of the overall probability mass with a relatively low temperature. And as you can see here, none of these models really reach perfect 100% level of language or confusion or accuracy. So even the best models still show some cases of this behavior on the monolingual setting. And we can furthermore see certain models like Llama 2 and Llama 3 and the Mistral models, which are especially affected by this language confusion across the languages that we tested. On the cross-angle setting, because this one now, instead of just basic conversational understanding, requires also more direct instruction following, right? You need to not only understand the instruction of the prompt, but also need to understand and follow the corresponding language instruction that is embedded in the prompt. And consequently, we can see here that all models do relatively worse on this, so slightly reduced performance. And we can furthermore see that certain models like Llama 3.1 and the initial Command R model actually struggle quite a bit with the setting compared to their monolingual performance. And for Command R, for instance, we can say that as we developed this model, for instance, we observed that these errors were taking place and put these evaluations in place, but were not able to completely fix this behavior in the initial release model. But the model that was later released, Command R+, already improved on this cross-single generation behavior quite a lot. And also the recently updated variants are doing much better compared to this initial Command R model. Now for the, just kind of to give you a general impression of the evaluation results, I don't want to have you look at like all these numbers here, but just kind of focus on one example row, for instance, which is Llama 3.1, just to illustrate a bit more what kind of patterns and behavior we can see across different languages. And in particular, I think the interesting distinction here is to distinguish between languages that the model has seen during post-training based on the tech report that was released by Meta, and the languages that it hasn't seen indicated in red here. And as we can see here, because all the languages that it has seen during post-training generally have values in the like higher 80s or 90s. So the languages that it has seen during post-training, the model generally does better on this cross-lingual instruction following setting. And comparatively, among unseen languages, it also performs better on Indonesian to the left here and Vietnamese. And both of those languages among these unseen languages are ones that, even though they're not spoken in Europe, actually use the Latin script. So there seems to be more transfer going on between Indo-European or Latin script languages, whereas the languages where it really performs poorly on in this evaluation are unseen non-Latin script languages. Yeah? So languages which use different scripts like Arabic, Japanese, or Korean, for instance, where the model in this instruction following setting does relatively worse. Now going to the word level results. In the monolingual setting, we can see again that some models are close to 100% performance on this setting again, but even the best models again still show some word level errors across all of the evaluations that we looked at. Furthermore, we can see in the cross-lingual setting, generally slightly reduced performance. And kind of the surprising thing here, perhaps, is that the Mixtral model is kind of the only outlier. So all models generally have relatively similar performance, with only the Mixtral mixture of experts model being relatively lower. And while we can't say exactly like what went into the model, I think one potential hypothesis could be that because this is the only mixture of experts model out of the ones we evaluated, that maybe some aspect of the token level routing in this model might make it worse or make it more likely to be able to have this confusion on the word level in practice. So it's perhaps a area for investigation when developing future mixture of expert models with token level routing. Now I just want to kind of share some additional insights with regarding the role of the dataset or the type of prompt that which play on the performance of this model here in the cross-lingual generation setting. And we can basically see that if we compare the kind of average performance or the general performance of all of these models on each benchmark, that overall the worst performance these models get is generally on these more complex prompts that we created. Whereas the Okapi and ChatGPT prompts are comparatively simpler. So the model struggles more with following these language instructions if it's already presented with quite a complex prompt in practice. The perhaps most interesting maybe insight from this study is really the impact and the role of instruction tuning of them on the model's performance. And I think the clearest kind of analysis here is basically looking at the difference and the impact instruction tuning or post-training has on different models. And to show that, we basically evaluated base models that you see at the top of each corresponding line segment and the corresponding instruction-tuned counterparts where they were available for open source use. And we were able to do that for the Llama and the Command R models, which had both instruction-tuned and base models available. And the interesting part here is that for the Llama models, we can see that the base models are actually doing very well on this task in the monolingual setting, right? So the base model is showing relatively little error on a line level for language confusion. However, after the models are further instruction tuned, their language confusion rates or the accuracy rates here plummet. So suddenly they show really high degrees of confusion, or in some cases are not actually able to really follow those instructions or generate in Arabic or those corresponding languages at all. And the main reason of that being kind of based on the communication from Meta is that for Llama 2 and Llama 3, the instruction tuning was mainly English-centric. So it showed very little or almost no data at all in these other languages. So the models really only learned to, regardless of the prompt that they get, to only respond in English. Conversely, we can see that the command models, the base models have relatively fewer or worse performance in this setting. But because for these models, we did multilingual post-training, they are now doing much better on this setting in a monolingual evaluation. So now I just want to add a bit more intuition for when these word level confusion errors actually happen in practice. And I think kind of one general thing or useful statistics to basically think about is the entropy or the model's uncertainty or confusion about what word or what token it should predict next. And again, given that we use nucleus sampling, generally the top tokens that are in this nucleus, so that are together allocated the majority of the model's probability mass in terms of next tokens. And we basically did an analysis across different prompts. So we observed this token level, word level confusion to happen. And intuitively, you can basically imagine that in order for models to show this sort of confusion, a token in an undesired language like English here needs to have sufficient probability mass to be sampled or to make it into this sampling nucleus, basically. And in practice, this essentially happens when there's not a single token or not like any few tokens that have very high probability mass, right? When a model shows very high confusion or high entropy among which tokens it should predict next. And when this sampling nucleus consequently is relatively large, so when there's relatively few tokens or more tokens that actually have like similar relatively low probability overall. And in those cases, it's where these models typically exhibit this confusing behavior. And because of this kind of analysis, we can perhaps also understand why certain cases like following complex instructions are more challenging because these types of prompts the model might have seen more rarely or maybe less calibrated or less knowledgeable about. So when it's generating this data, it may also get in kind of lower probability regions or higher uncertainty regions of its generation space, which makes confusion more likely in the end. Now, given that we've identified that this is an issue, there are certain ways that we can actually resolve or mitigate this behavior. And we can do this both at inference time, so we can try and adjust the sampling hyperparameters. Specifically, we can adjust the temperature, and by lowering the temperature, basically, we can make the distribution of the next tokens more sharper or more peaky. And so if the confused word is not in the the top next generated word, it's going to be less likely to be actually generated in the end. And as you might expect, you can see here that as we reduce the temperature, the confusion here on the word level gets worse. And if we increase the temperature, the model gets more confused in the end. We've also found that reducing the size of the nucleus has an effect, but a smaller one. And similarly, just putting more effort and more compute on the decoding, so allowing the model to explore kind of alternative, potentially high probability paths using beam search, also leads to reduced language confusion, however, at a higher computation cost. Similarly, and as I've already showed before, we can do things with the post-training data to make the model more likely to be less confused in practice. And here in particular, we've seen that actually just doing prompting, so just with the prompt, either one shot or 5-shot, showing the model the expected behavior, that this already helps a lot, in particular in the cross-single case, improves performance a lot for the base model. We can see the same trend that we've already seen for the llama models. If you actually use only English-centric post-training, that this has a negative impact and reduces or increases the language confusion the model exhibits. And kind of similarly, if we mainly use post-training data that has a decent fraction multilingual data in it, this generally has the biggest impact compared with future prompting. So for the main takeaways from this part of the talk, I mainly wanted to highlight that even though kind of this general feeling of, okay, can a model generate in the right language, at first glance seems fairly trivial and kind of obvious feelings. But specifically, if we actually look at these word level errors that the model makes, and given that even the latest generation or even that the latest models still exhibit these sort of errors, it's actually much more subtle and still a continuing limitation and something that we need to be aware of. As a general phenomenon, we can really see this as kind of a side effect of sampling, right? Of the model being too uncertain or too confused about what next token it should predict. It's also kind of a negative side effect of English-centric post-training, right? Where the model starts to overfit on this one specific language. And it's perhaps also an issue of the English tokens compared to tokens in other languages, perhaps not being fully calibrated, right? So the model not being fully, not assigning the correct magnitude of probability mass to tokens in these other languages. So they are not perhaps being as separated as they should be in the embedding space. And lastly, just want to highlight basically that this kind of the nice aspect of this language confusion behavior is that it's really comparatively easy and efficient to evaluate, right, compared to all of these more complex failings that models might show. And it's, I think, quite an important and useful sanity check to really make sure that models generate in the correct language, and then further ongoing, looking at actually the rest other factors like tone, hallucinations, right, coherence, so many more factors that we would want to evaluate and that make up kind of an ideal model response. So with that, I've shared a bit about how or some feelings of evaluating models in these like conversational settings. And now kind of just slightly shifting gears, we're still talking about evaluating multilingual models, but now in kind of settings using methods that are particularly important once if we want to make these models available to people across the globe. And here, really, the kind of main or one of the key criteria for making these models widely available is really making sure that they are both very good in terms of quality and performance, but also that they are very efficient to run, right? They need to be lightweight, they need to be scalable if people want to host them on their own compute, right? They shouldn't require huge amounts of computes and resources for them to run or to actually be useful to people. And if you look at the set of methods that people use to run these models on their own hardware or to make them more scalable in practice, one of the most common and widely applicable methods to compress these models into a smaller memory space and to improve their throughput is quantization. And however, to date, all studies in quantization really focused only on evaluating the performance of these models on English settings. And they also only generally looked at evaluating these models on automatic benchmarks, like some of the English benchmarks that I mentioned before, but didn't actually look too much at how these models look like when we ask humans if their generations are still good. So to give you a bit more context, quantization, basically, if you're not familiar with it, generally revolves around compressing the model's weights to a lower precision, lower bits representation. Quantization can be done in two different paradigms. You can train your model already with these lower precision representations, which is known as quantization over training, or you can try to apply this quantization post hoc after you've trained your model. So you have trained your model typically already in a higher precision floating point values, and now after the training, after you finished the model training, you want to deploy this model now using smaller memory in a compressed size, and you can use quantization also for this. And we focus on this setting because it's generally the most scalable setting. Weights of models would typically be released at higher precision, while practitioners would then create their own quantized versions of these models. For this post-training quantization, there's also two different ways that people typically go about quantizing them. One approach is just focusing on quantizing the weights of these models. And the nice thing about this is that this can be done completely offline, right? You just need to have access to the weights of the model. And you can then afterwards just load the compressed matrices directly from memory doing inference, which allows you to use fewer memory overall and also leads to faster inference in practice. The way this is typically done is basically by just using a scaling factor. That is where the main thing that is important here is just kind of the largest value, right? So the highest range, the highest magnitude of the values of the weights in your matrix that you then divide here by the number of bits that you actually want to compress it to, right? So if you want to compress it to lower bit representation, like 128 bits or 127 here, you divide it by this to now compress this larger value into your smaller range. And you basically just modify or multiply all the weights of your matrix now with this new range in order to get it or to be able to present these now with these 128 integers here. And in the end, you round it to make sure that you actually get an integer for representation. In practice, when you do this, you often realize, depending on the variance or how large the variance, how high the largest magnitude of your weights are, that just using a single scaling factor, right, for your entire huge weight matrix might not be sufficient. So instead, you can also do this on a per column level, right? You can, for each column, identify which is the highest magnitude, the highest value of your weights here, and use per column scaling factors now to do the quantization in practice. The other way that you can do this is you can not only quantize the weights, but the activations as well. And you would typically try to, again, compress the weights offline and do the quantization in practice. This can also be done on a separate training set beforehand. But if you do this on kind of held out data that is not really reflective of the test data that you want to evaluate the models on, can lead to poorer performance, which is why this is typically done on the fly. And if you quantize both the weights and activations, you can also make use of specialized operations on GPUs that use low precision matrix multiplication overall. Here again, kind of the setting is basically the same as before, just in the weight and quantization activation setting, we already can basically apply these scaling factors per column here for the weights and per token for the inputs here. But again, using kind of the same practice here, looking in the number of bits that we want for our corresponding representational range, and then compressing our the range of our weights and our activations into that range now. Now, just kind of highlighting that there's some difficulties in practice, particularly when we come to quantizing activations, which is that compared to weights, activations typically have a higher variance and a higher magnitude of their corresponding values. And in particular, prior work has also shown that for quantizing activations in some of the layers can often have outliers. Yeah? So most of the weights might have very low variance, while there may be certain outlier activation for specific tokens that have much higher magnitudes overall. And these, as a contrast, if you just try to truncate them into the same range, make this quantization a lot less accurate overall. And there are different methods like smooth quant here, which basically try to mitigate this issue by trying to migrate some of the difficulty or some of the variance of these activations to the weights instead. And in this case, basically, they just come up with a scaling factor that just looks at the corresponding maximum weights, maximum values in the weights and in the activations, that they then use to kind of scale down and compress the range of the activations. And in contrast, apply kind of the same multiplication, now the inverse of that to the weight matrix to make the variance of these weights now larger. And as a result, the weights are now slightly more difficult to quantize, but the activations are also easier to quantize overall. And as a result, you kind of get better overall weight and activation quantization together. So I just want to highlight this here in order to highlight a few of the challenges when quantizing and when evaluating these models, which can potentially lead to performance degradation in practice, because we might not be able to appropriately model these outlier dimensions in our activations. And so our model performance might suffer as a result in different languages. And so for here, the settings that we evaluated on, we basically used a couple of the methods and models from Cohere that we had easily available for quantization that I mentioned before, and looked kind of at a cross product of these different quantization settings, ranging from both 8-bit to 4-bit quantization with different methods using both these per column scaling factors, as well as kind of more fine-grained per group scaling factors, as well as for the weight and quantization, activation quantization, looking at both per column per token, as well as this kind of more advanced smooth quant method, and comparing this to the standard representation precision, which is half precision FV16 here. We looked at a couple of representative benchmarks, some of which I already mentioned before. So MLU for kind of question answering on exams, MGSM, which is this multilingual version of the GSM 8K math word problem dataset, Flores for machine translation, and the language confusion benchmark that we developed before, focusing on 10 different languages. And we additionally also wanted to get human evaluation results, and same as LLM as judge evaluations. And for this, we evaluated on an internal evaluation suite of complex prompts that we had developed and translated from English to other languages, as well as some public multilingual prompts in 4 languages that are shown here. Now, just kind of looking at some of the main observations and takeaways. of this evaluation here. Firstly, we can compare results across some languages for automatic versus human evaluation. And this is here the relative performance degradation when we compare to our baseline, right? So if the model had the same performance as our baseline, we would be at 0 here. And as the model's performance, so the 8-bit quantized model's performance gets worse, we see kind of percentage points decreases here relative to the baseline. So we can see that for the automatic evaluations across different metrics, we can see some performance degradation for English, for instance, or for Japanese. However, if we ask our human evaluation and look at these more challenging prompts, we can see that the performance degradation on these benchmarks is actually much more stark and much stronger for some of the languages that we evaluated, not really reflected in our automatic benchmark evaluation. So overall, we basically found that for when it comes to actually realistic generative conversational use cases, quantization and only looking at automatic metrics really underestimates the actual negative impact that quantization has in practice. We can also compare performance across different languages. And here, the main factor of variation is whether languages are Indo-European or use a Latin script versus the languages that do not use a Latin script. Again, Arabic, Chinese, Korean, Russian. And here we can similarly see for the languages that don't use Latin script that the performance degradation is comparatively worse across all the different language, all the different methods that we evaluated. And that can be explained both before, right? As we've seen, models generally struggle transferring more when it comes to transferring across different scripts, but also generally models have seen most of their data in pre-training either in English or in languages that also use the Latin script. So much more used and the vocabulary is much more tuned for these languages compared to languages that use different scripts, which are comparatively more underrepresented in pre-training. So we can really see a disparate impact for these non-Latin script languages. We can also look at the effect across different tasks where we can see where we kind of have the tasks ordered here roughly in terms of their how challenging they are, right? Going for the most simple or easiest tasks, which is language confusion or translation, right? As a relatively constrained generation problem, all the way towards more challenging evaluations like MLU, mathematical reasoning, and then this evaluation on true instruction following in real generative settings with an LLM as a judge setting or human evaluation. And we can see that here, as we get more challenging, that performance degradation gets worse with the LLM as a judge, potentially overestimating the actual negative impact here. So these challenging tasks actually are the ones that we see the biggest effect of quantization in practice. And now, finally, we can also look at the impact of, okay, how can we actually mitigate and improve quantization? And in particular, we can see here that for the method that I described before, right, smooth quant, which kind of uses the weights to smooth out some of these outliers that we observe in our activations, we can see that if we look at like the values or the colors of both those different lines, that like overall using smooth quant typically helps, except for MGSM where there's like some slight worsening in terms of performance. And we can also see here for per group scaling, if we if we kind of increase the granularity of our scaling factors and make them more fine-grained, this also improves our performance because we can now more reliably kind of model these outliers in our quantized models. So with that in mind, the main takeaways from this part of the talk are basically that I think as a community and generally for people like working in this field, I think it's really important to work on and to be able to serve low compute models or models in low compute settings to really make sure that they are as easy to adopt globally as possible. We've seen, I've shown that automatic evaluation really underestimates the impact of quantization. So in practice, I hope going forward that future studies that look at quantization really kind of go beyond just using these automatic metrics and also look at more challenging tasks. And we can also see that in order to really detect most reliably the negative impact of quantization, we really need to look at us humans. And that even for widely used 8-bit quantization methods, we can already see a negative impact that is perceptible by humans in practice. And I also hope, given that the disparate effect of quantization we've seen across languages, where some Latin script languages perform very well compared to other languages, I also hope that future work on quantization will look more in this multilingual setting, so that we don't invariably end up developing models that do much worse on some of these other languages. So with that, just want to share a few final thoughts on this. And I think a lot of work on evaluation, looking at these large language models, like I highlighted a bit in the beginning, right, in order to make sure that we have benchmarks that do not saturate, we really people have been coming up with more and more challenging benchmarks that are much more complex or test more complex types of behavior. And I think this is really important going forward in order to make sure that we continually push the frontier and continually make progress for developing more powerful large language models. But I think at the same time, we also need to kind of look and make sure that we don't develop any blind spots and make sure that we at the same time it has also fundamental capabilities of conversational understanding, of reasoning, of different types of model behavior, and make sure that our models don't end up performing these sort of sophisticated tasks while in the end maybe performing shortcuts cuts or failing on much simpler problems. I hope I was also able to communicate that in some settings, while automatic evaluations have a lot of benefits, right, they're much more scalable and much more easy to run and easy to compute. In some settings, they're not sufficient to give us the full picture or the full story, right? So in order to, we still also need to be aware that there's still a role for human evaluation if we really want to make sure of a certain type of behavior or certain type of comparison. And that even though, given the point that I mentioned initially, that most benchmarks to date that are well used are based on translation, that I hope that also as a community for developing these multilingual large language models, that we go beyond simply using translated benchmarks, because I think that will be really important to make sure that these models are actually useful and applicable and representative of people and users around the globe. So yeah, that's it for my presentation. Thanks so much for your attention, and I think we have some time for questions.
Yes, we do have a session for question and answers right now. Thank you so much for the presentation, Sebastian. I personally think that the LLMs are the most the misunderstood topics in deep learning recently because of all the hype and everything. So thanks so much for this mystifying this topic and explaining to us how all this work. We have questions from the public. I'll read Samuel's question. He says, what are the biggest challenges today in using the great foundation models, more specifically speech, to produce content in Brazilian Portuguese? I will send
Cool.
it.
Yeah, good. Yeah, good question. I mean, so I think, I mean, overall, yeah, I think that's one question for like foundation models, which have, I think, so far a lot of them have focused more on like text or images, right? And then also for speech overall, which opens up like a lot more applications or a lot more usage scenarios. I think with regard to different languages like Brazilian Portuguese, for instance, I mean, I think generally for all of these models, like in general, it's often the availability of like high quality data, right? You might have seen that given kind of the huge amounts of data these models are pre-trained on, we are starting like some of these models. So for pre-training specifically, we're starting to hit the limits of what data is easily available online. So I think going forward, getting still like high quality data, particularly in other languages that maybe are not represented that much as English online, is kind of a key challenge. Similarly, like in post-training, actually being able to align or properly train these models for the types of behavior, values, like objectives or kind of key instruction pulling behavior that we would want is still something that yeah, people are figuring out how to train these or like fine tune these models in a better way. And then also I think for speech, right? I think this is still kind of a such an open space, right? There's been only recently with I think with Gemini, with GPT-4o, right? Actual applications of like real-time interactions and real-time speech and conversations with these models. And yeah, there I think as a community we don't really have any good benchmarks on like the speech setting to actually be able to evaluate the yeah, the extent of this like human level conversational right. So if you account for interruptions, uh, pauses in speech, kind of naturally flowing conversation. So far, we've had benchmarks for very static settings, right, like speech transcription or generation, like speech synthesis, but actually for simulating or creating these like very human-like conversations, like how do you even evaluate different aspects of this type of behavior? So I think as we go towards these more complex settings on the evaluation side, there's going to be lots of challenges, and then similarly looking at how getting the data, training the models to exhibit or to really would be able to work with people in the way that we would want for different applications is it's going to have its own challenges depending on the application domain.
Okay, we have another question from Birgit. She 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 said here, what resources are used to train multilingual LLMs?
So in practice for training these multilingual language models, it's very similar to what you probably or what you might maybe think even for training English language models. So typically it's a lot of yeah, data that is being either scraped or used from existing web repositories like Common Crawl, so snapshots of the internet that is then kind of processed, maybe filtered, and ultimately fed into these models. And this data is really huge, right? It's much more than anyone here or anyone, I mean, maybe even like the entirety of Brazil could consume in their lifetimes, right? These models like Llama trained on 10, 15 trillion tokens of data. So these are really like, yeah, amounts of data that kind of boggle the imagination. And then for on the post-training, right, there's pre-training, training models that have a very strong understanding of natural language. And then in post-training, it's where you would try to make these models better at instruction following and being able to actually fulfill different tasks that you would want to do with them. So this requires kind of more human annotation of creating the types of data that you would want these models to accomplish in the end. So there's a lot more human annotation or synthetic data generation where models are also created to expand this pool of post-training data that is being used there. And as you go beyond other modalities, right, beyond text, like images, you then need to not only get image data or like use cases for that represent text, but also with images or with video, right? So you can imagine the kind of scope, both in terms of like getting that data and also getting data that is representative of what you want these models to do, but also making sure that you don't have data that is like toxic or that allows the model to generate a language that is harmful. So also ensuring kind of safe usage and like safety of this data is very important.
Very good. I have a question myself here. How do how do you address data bias when training multilingual models? Like uh, some languages have more data than others. How do you train this model with these different amounts of data?
Yeah, I mean, typically you want, I think you want to start with some evaluation, some metrics that you want to optimize that you care about, ideally representing different languages. And then I think in practice, the question is really an empirical one. So you would typically update kind of the weights of your data, right? How much you sample from your different languages or from the different data sources in order to kind of maximize whatever you care most about, right? If you maybe you care more about certain languages, in which case you might, in the end, it might be beneficial to have the model see or sample more of that data more frequently, or you might want to have a model that's better in English, so you care less about its other languages, or some model that is like reasonably uniform across all the languages. So yeah, I think a lot of this is basically just kind of trial and error experimentation in terms of making sure that you have enough data in each language, and then kind of adjusting and experimenting with different ways to like sample or to filter the data to ensure each one is high quality enough and that the relative distribution is kind of appropriate for your target setting.
Very good. Thank you for that. We have another question from Joel here. He said, just by curiosity, what's the thought process behind elaborating quantization methods?
Behind this, so I'm not sure I fully understood behind elaborating quantization methods.
Yeah, frankly,
But behind more advanced quantization methods, or behind quantization methods in general, or yeah.
uh, Joel, if you could like
Yeah, I think, I
explicitly,
mean, yeah, I
yeah,
can, I mean, yeah, correct me, right, if I'm on the wrong track. I mean, for quantization methods, I hope in general, right, hopefully I was able to convey that because like these models have so many, right, billions of parameters. So in order to run them, you need GPUs or multiple GPUs with enough memory, right, if you want to use them actually in the full FP16 precision. So in order to use like less space, less memory, you want to represent them with like fewer memory with only like 8 bits or like in a smaller space, so you can run them on like less hardware, right? So this is just kind of from a even if you have a lot of compute, you still want, in order to use this more effectively, right? You still want to quantize your models, and yeah, for the more advanced methods that I mentioned, right, a lot of this was basically just dealing with these like outliers or with the changing variance in terms of your weights in order to introduce these different scaling factors, or maybe yeah, counteract, mitigate some of the negative impacts by trying to squash some of these outliers to a very small range for the quantization. And I think that that is basically what a lot of these metrics, which or methods, which are often like heuristic based, right, coming up with different ways to get your scaling factors, or what they're based on in general. So hopefully that was able to answer the question. If there's anything else, feel free to follow up.
I think we have the last question here from Joel as well. Uh, he he said, "Is it um, is it somehow a possibility to incorporate sign language to these multilingual models?"
Cool. Yeah, great. That's a great question. I mean, yeah, it's sign language in terms of right. Its modality, right, requires like visual, image, or like video processing, even, right. So it's something that is has been like traditionally not such a main focus in the like NLP community, but recently actually there's been more interest in sign language processing, and there've been and the main kind of bottleneck for getting like real models being able to model and process sign language has been data. There have been recently a couple of like high quality sign language data sets. And so in practice with that data, and given that models might also are exposed to sign language like doing pre-training, that should generally be possible. I would imagine, I mean, I actually be curious. I could imagine that some of the recent models, maybe for at least the basic signs, I'm not sure for like the full understanding, might already be able to, if you show them a given sign, might be able to tell you what that means, because they might have seen pairs of the signs and their its meaning already during training. But you could definitely like fine tune or like train these models more if you show them like data with sign languages. There are also approaches, right? Sign language has its internal structure too. So if you want to do this in a more data efficient way, you could try to exploit biases or structure in that and kind of embed that in your model to train like a smaller model just for sign language. But that would of course not work kind of at scale for this large language model. So that's a really very promising area, definitely really useful to make these types of like models or this kind of technology like more widely available.
Very good. We have a question from Louisa. Um, how can people contribute to multilingual research advancements, even if they don't have strong technical backgrounds?
Yeah, I mean, great points. I think in practice, one good way, for instance, could be to get together with like-minded people, right? People you know from your university or your research group, or people that you know who have a shared interest in contributing in this space. There are for some communities or languages, like over the last years or even before then, they have different like grassroots efforts come up. So there are communities dedicated to developing models or for African languages or languages in Southeast Asia or Indonesia, in Turkey, like across all kinds of different like languages and countries, and really kind of advancing the evaluations, resources, models available in those languages, and people kind of finding and collaborating with maybe some people who have more technical experience working with people who know more about the data, the linguistic side, and kind of working together there across like larger projects. Also, there are other wider initiatives, Cohere for AI, this research lab from Cohere. They have been doing a lot of community initiatives. Many of them have furthering the multilingual capabilities of the models at heart. So these AYA models that I mentioned, for instance, in the beginning, have been the result of a year-long collaboration between 100 plus people across a lot of different countries, where also many of them contribute in different ways, from annotating data to reviewing or evaluating model responses, and some helps more with modeling. So I think the important thing is just to kind of think about what really excites you, right? Do you care about your language or about some other language, or just about the multilingual agenda like overall, and then look for either you can ask, you can write to people like me or people that you maybe seen in the community, which are often generally happy to help and to point you kind of in the right directions of initiatives or efforts or existing groups that you can get involved with. And yeah, I think it's particularly useful in places where maybe you don't have such a support network or that many like research groups available like directly around you, or in university, where I think it can be really helpful to connect more broadly, right, in your country or beyond with other like-minded people. And I do think it's worth kind of looking into that.
Amazing. I'll read the last question because we are kind of running out of time. So, question from Samir. How do you see the future of multilingual LLMs in the sectors like TV, entertainment, or news? I've noticed that there are already several LLMs streaming content in the streaming industry.
Cool. Yeah, good question. I mean, I'm less familiar with those application domains personally. I mean, yeah, you could imagine things for like multilingual LMs. I think one of the coolest application, for instance, is to do like automatic dubbing or automatic subbing of like news podcasts. Right, you can imagine any like news story in any language being directly kind of converted, and also the speaker movements being directly updated to coincide with the new language, right? So having this kind of translation, like fully end-to-end multimodal translation, I think is a really cool application that would enable not just for news, but any kind of content, right, to make that more widely available. You could, yeah, I mean, as part of the news industry, right, you could use these as like research assistants, right, where that help with journalism. They can help people like writing, or so that a lot of the kind of for domains like sports coverage, for instance, where there's a lot of like road or template coverage, you could automate like a lot of these simpler things with LLMs so that humans and journalists actually can focus on more interesting coverage or kind of more interesting stories. So I see these models more just as a way to like work with people, like to support, to assist people in the work, and kind of to free people's time for kind of more meaningful to more valuable work that they could be doing. Oh, I think you're muted right now.
Oops. Thanks so much, Sebastian, for the talk. Was an amazing talk, very clear. Thank you so much for participating.
Yeah. Thanks so much for having me, and I hope you have a great rest of the Understanding Deep Learning workshop here and program. And yeah, wish you all the best, and all the best in all your research or data science endeavors.
Thank you so much. Bye-bye. Oh, I forgot to mention a detail here. We will have another talk in a few minutes, in actually 30 minutes. So stay tuned. Um, we'll have a talk from Jeremy Ben. He's a researcher from MIT. He will talk about metrized deep learning. So follow. I'll put the link of the next live section here in the chat. So see you soon. Bye bye.